Hi developers! In this video, we're going to show you how to profile models using Qualcomm Neural Processing Engine SDK. In this video, we'll discuss features available in the Qualcomm Neural Processing Engine SDK that can help profiling model execution on hardware accelerators. Before we begin, let's make sure we have a few prerequisites in place. First, set up the Qualcomm Neural Processing Engine. Second, convert a neural network model to a deep learning container or a DLC file format. DLC is a proprietary file format used by Qualcomm Neural Processing Engine. It acts as an intermediate representation of your model. Optionally, you can quantize the converted DLC file to int8 or int16 data format for enhanced performance and efficiency. If you are profiling the execution of your model on the hexagon tensor processor, then you must complete the graph preparation step as well. This ensures all the necessary optimizations are baked into the DLC file before deployment. Finally, to profile the execution of your model, we will use the snpe-net-run tool. This command line tool prepares inputs and input list.txt file with all the information to profile the model execution accurately. On the device side, you should sideload Qualcomm Neural Processing Engine binaries like snpe-net-run, snpe-diagview, etc. Sideload all necessary Qualcomm Neural Processing Engine libraries and HTTP-specific libraries like skeleton library. Finally, make sure to set the environmental paths including path, LD library path, and ADSP library path. Before we get into profiling models, let's take a high-level look at the workflow of Qualcomm Neural Processing Engine SDK. A developer or a machine learning engineer will train their model using a training framework like TensorFlow or PyTorch. Once the training is complete, developers will then export their model to have static weights and biases. For example, a model trained in PyTorch could be exported to ONNX, or a TensorFlow model could be exported to a TensorFlow-like model format. Now, this exported pre-trained model is fed to the tool provided by Qualcomm Neural Processing Engine SDK, so it can be deployed on devices with Qualcomm Technologies processors. First, we'll use Qualcomm Neural Processing Engine SDK tool to convert the pre-trained model to DLC format. Next, we quantize DLC target hardware accelerators such as HTTP. Finally, we'll use a tool such as snpe-DLC graph prepare to target specific HTTP on a device with a Qualcomm Technologies processor to optimize the model execution. We can then deploy this optimized model to the target device to efficiently run on hardware accelerators. We will now profile model execution on devices using some of the tools shipped as part of Qualcomm Neural Processing Engine SDK. The main tool we'll use is snpe-net-run. The snpe-net-run tool is a command line binary app that has been written using Qualcomm Neural Processing Engine C APIs. The functionality of this tool is to load a DLC file, a set of input images contained within a text file, and execute the model on these inputs on a selected runtime. Common arguments to snpe-net-run tools are: container is the path to DLC model file, input list is a text file with paths to pre-processed input images, output directory is the path to save output tensors after performing inference. Use GPU, use DSP, use AIP are flags to set runtime to execute model. Profiling level is the argument to set granularity level at which of profiling is done. Performance profile specifies performance profile value that may affect power versus performance trade-off. User buffer TF8, user buffer TFN provides input-output buffers, avoids an extra copy of input-output buffers. After executing the model on provided inputs, the snpe-net-run tool will save the output tensors as binary files to specified output directory. Based on selected profiling level, the tool will write model execution diagnostic data to a file called snpe-diag.log to the same output directory. Now, let's look at a graphical representation of the snpe-net-run tool workflow. First, the snpe-net-run tool loads a model in either floating point 32-bit format or quantized DLC format. It also loads an inputless text file that contains paths to preprocessed image data into the device. Next, the snpe-net-run executes the model based on the provided inputs sequentially on selected runtime. After execution, the snpe-net-run tool writes inference results or output tensors to the specified output directory. Simultaneously, the Qualcomm Neural Processing Engine writes a diagnostic file, snpe-diag.log, to the same output directory. Now, let's take a look at a working example of snpe-net-run tool. First, we load a model.dlc along with a target raw list.cast file that contains paths to preprocessed images we would like to use for inference. Next, we set the runtime to DSP to execute the model on HTTP. In addition, we set the performance profile to burst mode to achieve best performance at the cost of power. Lastly, we set profiling level to detailed. This will generate a detailed diagnostic data in the snpe-diag.log file to specified output directory. Here's the result when you execute the model using the snpe-net-run tool on target. Upon completion, snpe-net-run tool will write out all the output tensors for each input image to their own respective directory in output directory. In this example run, here is what we will see in the output directory. As mentioned earlier, if the profiling level is set to detailed, the tool will write model execution diagnostic data to a log file, snpe-diag.log. This log file contains performance metrics that will help us understand the model execution on a hardware accelerator. The diagnostic file, snpe-diag.log, is a binary file that can only be read by a specific tool called snpe-diagview. This tool is included as part of Qualcomm Neural Processing Engine SDK. Now that we have a profiling log file, let's talk about how we can view the contents within this log file. As mentioned earlier, the profiling log file is a binary file that can only be viewed with the help of a tool called snpe-diagview. This tool is shipped as part of Qualcomm Neural Processing Engine SDK, and is a command line tool written using Qualcomm Neural Processing Engine C APIs. This tool takes a diagnostic or profiling log file and output diagnostic data in human-readable format. This binary executable file can only be run on a host machine the device is connected to. So any profiling or diagnostic log file must be copied back to host machine to use with this tool. Here are the command line arguments this tool takes. It takes an input log file as a mandatory argument. Optionally, this tool takes an additional arguments that display the readable output to a CSV file or to write the content to a Chrome trace JSON file. Now that we know how to generate a snpe-diag.log file and then view contents within the diagnostic log file using snpe-diagview tool, let's see the performance metrics the data provides. The tool returns several metrics as shown here. Load measures the time required to load the model's metadata. Deserialize measures the time required to deserialize the model's buffers. Create measures the time spent to create Qualcomm Neural Processing SDK networks and initialize all layers for the given model. Init measures the time takes to build and configure Qualcomm Neural Processing SDK. Deinit measures the time it takes to deinitialize Qualcomm Neural Processing SDK. Create network measures the total time requires to create all network for the model. RPC init time measures the entire time spent on RPC and accelerators used by Qualcomm Neural Processing SDK. Snappy accelerator init time measures the total time spent by Qualcomm Neural Processing SDK to prepare the data for the accelerator process, such as GPU, DSP, AIP. Accelerator init time measures the total processing time spent on the accelerator core. Here we see the average snappy execution statistics, which includes total inference time, measures the entire execution time of one inference pass. This includes any input and output processing, copying of data, etc. Forward propagate measures the time spent executing one inference pass, excluding processing overheads on one of the accelerator cores. RPC execute measures the entire time spent on RPC and accelerators used by Qualcomm Neural Processing SDK. Snappy accelerator measures the total time spent by Qualcomm Neural Processing SDK to set up processing for the accelerator. Accelerator time measures the total execution time spent on the accelerator core, which may include different hardware resources. And here we see the per layer stats returned as part of the diagnostic data. Each row in this section specifies operator ID, operator name, and total number of cycles spent executing the operator. Execution time is specified in average number of cycles spent at each layer. Each row also specifies the hardware accelerator the operator has executed. Here is a visual representation of important metrics such as total inference time, forward propagate time, RPC execute time, snappy accelerator time, and accelerator time. snpe-net-run tool loads a DLC and creates an instance of network to execute a set of input images. However, this instance will execute images sequentially and there is no asynchronous execution. Between each inference, there may be a slight idleness on the hardware accelerator. Hence, we may not be able to achieve peak throughput in terms of performance when using a tool like snpe-net-run. To achieve peak throughput, Qualcomm Neural Processing Engine SDK provides a tool called snpe-throughput-net-run. snpe-throughput-net-run is a multi-threaded application that creates multiple instances of the same model, running each instance within its own software thread. With multiple threads running, the application will reduce the idle time on the accelerator. This tool can also simulate concurrency scenarios when running multiple models. To create multiple instances, the user must specify the arguments repeatedly to configure each instance. Here are some common arguments that snpe-throughput-net-run tool takes. Container is a path to DLC model file. Duration is the number of seconds to run the model. A random set of input images will be generated before inference. Use GPU, use DSP, use AIP are flags to set runtime to execute model. Performance profile is a specified performance profile value that may affect power versus performance trade-off. User buffer TF8, user buffer TFN provides input-output buffers. It avoids an extra copy of input-output buffers. Let's look at an example of executing a model using snpe-throughput-net-run tool. In this example, we execute model.dlc on DSP runtime, that is HTTP hardware accelerator, for a duration of 30 seconds. We also set the performance profile to burst mode to achieve best performance. We also leverage user buffers to pass input-output buffers. During execution, the tool will create an instance of model and execute this instance in its own thread, that is thread 0. After executing model on hardware accelerator for the specified duration, the tool returns throughput achieved. Now, let's look at an example that demonstrates two instances of the same model executing using snpe-throughput-net-run on HTTP. In this example, we create two instances of the same model.dlc. Please note, to create multiple instances, we just need to repeat the same set of arguments to snpe-throughput-net-run tool. In the first instance, we load model.dlc to run on DSP runtime for a duration of 30 seconds. We set the performance profile to burst mode and use user buffers to read and write to input-output data. We use the same configuration for the second instance as well. We load model.dlc to run on DSP runtime for a duration of 30 seconds. Each instance gets created and executed in its own thread. While instance 1 finishes its execution and revokes its resources, instance 2 is ready for its own execution as inputs are loaded asynchronously. Input data is readily available for instance 2 to begin its execution. Execution will ping-pong between these instances that eliminates any idleness on the hardware accelerator, thus improving overall performance. In this example, for a single instance from the previous example, we know the model achieves around 338 inference per second. With 2 instances, we can see the overall peak throughput has increased to around 356 inference per second. Some additional notes to keep in mind. Adding more instances may yield better throughput until a performance plateau is reached, after which adding more instances won't improve peak throughput, especially for smaller models, which may benefit more from adding more instances. Larger models might not show any significant improvements. Adding more instances comes at the cost of resources. That is, adding another instance will consume more memory. So far, we looked at how we can check the performance of models in Qualcomm Neural Processing Engine SDK and its tools. Now, let's look at one more feature that helps us understand the performance of a model: Linting Profiling Mode. Linting Profiling Mode provides more granular profiling data for models running on HTP. In previous profiling levels, we know relatively how much time or number of cycles spent at each operator within a network. It doesn't provide information on any op parallelization details. As HTP can execute operators in parallel using HVX, HMX intrinsics, it makes more sense to check if there are any ways we can further optimize the parallelization of operator execution. Linting Profiling Mode gives us insights into such profiling data so we can understand how HTTP schedules operators within the model and possible ways to optimize if there are any bottlenecks. Here are a few details about Linting Profiling Mode in QNN. Reports generated have per-op profiling results in cycles spent instead of time in microseconds. There is no direct conversion methods from cycles to microseconds, so we will use relative number of cycles spent at op for comparison. Chrome trace can be exported from linting profile data for visualization. Linting mode can be activated by providing profiling level equals linting in snpe-net-run tool. Programmatically, we can use Snappy, Snappy Builder, set profiling level API to set profiling level to Snappy profiling level linting mode. Linting profiling report provides the following entries per op. Cycles, number of cycles spent executing the operator on the main thread. Wait, the wait entry reports the number of cycles spent waiting before op execution on main thread begins. This wait period can be attributed to various factors, such as scheduling or waiting for some background HVX or DMA activity to finish. Overlap. The overlap entry denotes the number of cycles spent on at least one background op while this op is executing on the main thread. Overlap wait. The overlap wait entry denotes cycles spent on at least one background op while the main thread was waiting. Resources. The resources entry lists the different resources used by the given op, namely some combination of HVX, HMX, and DMA. Here is an example of how we can invoke the linting profile mode using the snpe-net-run tool. In this example, we're executing Inception v3 quantized model on a set of inputs contained within target raw list.txt file on HTTP using DSP runtime. To set the linting profiling mode, we use profiling level to linting as highlighted. Once snpe-net-run tool completes its execution, The tool will save linting profiling data as part of snpe-diag.log file within specified output directory. To view this data, we'll use snpe-diagview tool on host machine. Pull or copy the snpe-diag.log file back to host machine using ADB or SCP. Once the snpe-diag.log file is available on host machine, we can then use snpe-diagview tool to write linting profiling data to a Chrome trace JSON file, which we can then visualize using a Chromium browser. To generate Chrome trace, here is a sample command. Note, we specify Chrome trace to indicate snpe-diagview to write linting profiling data to Chrome trace JSON file. Once this JSON file is written, we can use either Chrome or Edge browsers to visualize Chrome trace. For loading a Chrome trace JSON file into a Chromium browser, visit one of these websites. Here is an example of what Chrome trace will look like in a Chromium browser. Chrome trace shows both foreground and background op executions. For each op, we should ideally have a good overlap indicating parallelization. So far, we saw how to use a linting profiling model to generate up-level profiling metrics, including foreground and background operator executions. Now, let's use linting mode to see if we can optimize a model by looking at an example. In this example, we have a very shallow neural network model in ONNX format. The model has two intermediate branches, each branch performing a couple of convolutions before the results are used in a sub-operator. We'll show how this sub-operator would be a bottleneck when executing this model on HTTP using linting profiling mode. To begin, we'll follow a typical Qualcomm Neural Processing Engine SDK workflow. First, we'll convert, quantize, and prepare models to run on HTTP. Next, we'll execute the optimized model DLC on HTTP using snpe-net-run tool on a set of inputs with linting profiling mode enabled. Finally, once snpe-net-run completes and diagnostic or profiling log file is written to output directory, we'll copy the log file back to host machine and use snpe-diagview tool to generate a Chrome trace JSON file to visualize linting profiling data. In Chrome trace, the sub-operator with op ID 57 takes significantly longer to execute and doesn't have much overlap time with the background op. Given the op parallelization is not significant, we can categorize sub-op execution as a bottleneck. Let's see how we can optimize this model to see if we can improve performance of this model. Clearly, sub-operator is inefficient as it predominantly runs on HTTP using HVX resource. To remove this bottleneck, we apply two optimizations. Optimization number one, instead of two branches, each performing a couple of convolutions, let's merge the two branches into a single branch. This can be done by modifying the convolution operation. Optimization number two, after merging two branches, there is no need for a sub-operator. We replace the sub-operator with another convolution operator to yield an equivalent model. After applying the two optimizations, we can profile the model again. Note, if we change the architecture, the model may need some retraining. Once again, we go through the typical profiling workflow. We convert, quantize, and prepare the model to run on HTTP. We then execute the model on HTTP using snpe-net-run tool with linting mode enabled. We then use snpe-diagview tool to generate Chrome trace for visualization. Here is the equivalent model and its Chrome trace. With the updated model's linting data, we can clearly see that there is a better parallelization. That is, both foreground and background op execution has relatively significant overlap. Looking at other metrics, such as total inference time, etc., we can observe that the model can run faster now compared to previous version of the model. Thus, we can conclude that we have removed the previous bottleneck with the help of linting profile data. Performance of model can be tuned with the following parameters. Ensure depth of hidden convolution or activation layers is a multiple of 32. Use input batching to improve performance. Appropriate batch size for a network depends on the model itself. Use Performance Profile API to check power versus performance trade-off. Burst mode gives best performance as the clocks are bolted to Turbo L1 mode. With this, CPU wouldn't enter into deep sleep. Using detailed or linting profiling modes may impact performance of operator or model as more detailed diagnostic data is collected. User buffers will eliminate an extra copy of input-output buffers from and to model execution. Use snappy initialization cache mode to ensure models can be loaded quickly upon subsequent runs. Now that we know more about the purpose, functionality, and implementation of profiling models, you can start profiling models on your device using Qualcomm Neural Processing Engine SDK.